In 212 BC, during the siege of Syracuse, legend has it that Archimedes deployed giant curved mirrors along the coastline. By catching the sun's rays and angling them toward the encroaching Roman fleet, he concentrated the light into a single intense beam, igniting the wooden ships before they could reach the shore. That exact physical property drives modern communications. The deep parabolic curve of a satellite dish captures scattered incoming signals and bounces them toward a single, highly concentrated target. You can test this yourself. In about 5 minutes, we are going to build a DIY tabletop optics lab to map how light moves and physically prove the mathematical laws of reflection. To run this experiment, you need 5 basic items: a standard concave mirror, a roll of measuring tape, an unlit candle, a V-stand, and a small square of white paper. Setting up this simple bench takes these concepts off the chalkboard. You get to physically manipulate light and verify the laws of physics with your own eyes. Step 1 starts outdoors. Take your concave mirror and that small piece of paper out into direct, bright sunlight. Hold the mirror so it catches the incoming sun rays. Then place the paper in front of it. Slowly move the paper back and forth until the wide wash of reflected light sharpens into the smallest, brightest dot possible. This chart shows what is happening in your hands. The curved mirror takes incoming parallel light rays and bounces them inward to a single intersection point. In physics, this is the focus. The distance from the mirror to that point is the focal length, f. Take your measuring tape and record the physical distance from the center of the mirror's surface to that bright dot on your paper. Write that number down. This measured focal length is a fixed physical property of your specific mirror. It provides the baseline value for every calculation we will perform indoors. Head back inside to a dark room. Lay your measuring tape perfectly flat across a table. Using the V-stand, place the concave mirror upright exactly at the 0 centimeter mark. Before we light the candle, we need to avoid the most common mistake with this setup: accidentally blocking the light source with the paper screen. This illustration shows the correct physical configuration to prevent that block. You must ensure the candle flame sits slightly above the mirror's horizontal center line, and the paper screen sits slightly below it. Light the candle and place it at a far distance on your measuring tape, say 60 or 70 centimeters away. Now, take your paper screen and slowly slide it back and forth along the tape between the mirror and the candle. Keep adjusting the paper until the blurry smudge of light snaps into a crisp, sharp, upside-down image of the candle flame projecting directly onto the page. Capturing that upside-down flame proves that real images are not optical illusions, but actual physical projections formed by light rays converging in space. We need to track 2 specific variables on our bench. The first is the object distance, which we denote as U. This is the physical distance from the mirror to the candle. The second variable is the image distance, denoted as V. This is the distance from the mirror to the paper screen where that sharp image has formed. Looking at this table, you can see how we log our data. Write down your first set of U and V measurements, and make a note that the image state is inverted. Next, pick up the candle and move it 10 centimeters closer to the mirror. Repeat the process. Slide the screen along the tape until you find the new location where the sharp image forms, and record those new numbers. As you continue this process, a clear physical trend appears. As the candle moves closer to the mirror, the image distance increases, and the reflection on the paper becomes physically larger. The movement of that image follows a strict rule. There is an inversely proportional relationship between exactly where an object is placed and exactly where its reflection will form. This equation is the mirror formula. It maps the precise relationship between the physical distances you just tracked. Before calculating, we must apply the sign convention. Because your tape measure is opposite to the incoming light, both U and V must be entered as negative numbers. Let's test it. Take one set of your measurements, for instance, -40 for U and -24 for V. Plug them into the formula and solve for F. When you finish the calculation, your resulting number should match the physical focal length you measured outside in the sunlight during step 1. The math perfectly models the physical bench. This formula doesn't just exist in a textbook, it accurately predicts the behavior of the light you manipulated on your desk. Over the course of a few minutes, you have captured a focal point, mapped real-world image tracking, and used hard data to verify the laws of reflection. Because you have verified these mathematical rules, you now possess predictive power. You can calculate exactly where an image will form for this specific mirror without ever needing to light the candle. As this diagram shows, you can apply this practically. By taking your mirror back outside, you can build a mini solar cooker, placing a small combustible item exactly at your mapped focal point to catch the concentrated energy. Understanding how to model light mathematically means you no longer have to guess where a reflection will land. You can build a setup, run the numbers, and put that light exactly where you need it.